Isabel Valera from Max Planck, who will tell us about fairness and interpretability. Thank you.
Hello. So thank you very much for having me here today. Hello to everybody in every corner of the room. Hi. This is quite of an interesting setting, so I'm not sure how I'm going to fit here. So in the next 2 days, we are going to talk about fairness. I lost it, now better. Okay, a bit of interpretability. So, but before entering into why fairness and interpretability, let's have a bit of a motivation. I think probably everything that we are going to see in the next 5 minutes you are aware of, but I think it's always good to refresh. So, I think most of you know that by now, machine learning methods are almost everywhere in your daily life. So, for example, they may have an impact in the products that you buy, for example, online, even in how you spend your spare time, how you access information and which information is presented to you and in which way. Also, I'm not sure how many of you have been dealing already with that, but also whether you apply for a loan and you get it or you don't, the price of your car insurance, your health insurance, quite a few, quite important settings. And in some other scenarios, they are even there to assist in the diagnosis of some disease. So basically, in summary, what I'm trying to say here is that machine learning is nowadays more and more there to assist or even to replace human decision making. And this is happening in many scenarios, including banking. We talk about loans, insurance, we talk about health insurance, car insurance, even security, reviewing systems, which is quite important for scientists like I am, or recruiting. So if you apply to a very large company, I guess if some of you are computer scientists, Amazon, Facebook, Google, they have filtering systems that are automatic and decide whether you get visible or not for the company. And even, probably none of you has been exposed to that, but even in court. So some decisions about how risky it is to have you around. If you are a criminal, they are also decided by machine learning. Of course, together with this deployment in the real world, there is a rising number of concerns that are arising as we see machine learning more and more in the real world. Here I have a small snapshot of some of the news of the last 2-3 years, where basically machine learning is being blamed for having some discrimination patterns or presenting some lacks of privacy. Also, they challenge their lack of explainability. I think particularly important since we have more and more deep learning. Even in the case of the European Union, there is this new GDPR, which is a privacy law that actually talks not only about privacy preserving machine learning, but they also talk about the people of having the right for an explanation every time we use machine learning to make a decision about their lives. Or I think this is from February. There was an article that was blaming machine learning to be causing a crisis in science in general. Right? So it seems to be that there are some social concerns here. So on the other hand, this has had an impact also in how the machine learning community has been evolving in the recent years. So here I got some pictures from Moritz Hart from Berkeley and also Finale Doshi from Harvard about how the number of papers in both topics, fairness here and interpretability here, has been growing in the recent years. So basically, if you see, like early in the 2010s, there were almost no papers in any of these two topics. In the case of fairness, we have seen an exponential growth in less than 10 years. And in case of interpretability, the growth is not quite there exponentially, but it's growing also significantly. So it seems that all these social concerns are coming up also with some efforts from the machine learning community trying to address them. Here I only talk about fairness and interpretability, but other topics like privacy and accountability, any social challenge that you can think of has been also being addressed. So just for your information, I have created a GitHub where I have uploaded some of the slides. I will finish uploading them tomorrow morning in case you want to have access to them. I'm going to start upside down or in the other way around, and I'm going to say that the main take-home message that we all should have before we leave this room tomorrow is that while in computer science and in particular in machine learning, we usually assume that we are given with some data, we fully try. Okay, I'm not sure why I get on and off. Okay, so basically, while in machine learning, we mostly assume that we are given with some data, which we believe blindly in general, and everything that we most of the time, or for many years, we only worried about was about the methodology, which classifier to use, prediction error, accuracy, reward. Something that we have been ignoring for a while has been how these features that are representing our data has been collected and how this data has been collected. And this is something that I think that as we deploy machine learning in the real world, this is something that we cannot forget. So the main message of these talks, and we are going to go through a path that's going to bring us to this message, is that measurement and data collection should be always kept in mind when we are deploying machine learning in the real world, and especially when the applications for which we are using these methods may have important consequences in people's life, like the scenarios that we were talking about before, right? So far, I don't think there should be any questions, but I'm happy to take any questions during all this process. If I don't see you, say something. And as I promised, what we are going to do is that we are going to start with fairness. So in the next hour and 20 minutes, and tomorrow for quite some time, we are going to mostly talk about fairness in machine learning, what fairness means in that context so far, and what efforts has been done, and also some challenges. So before I gave you a snapshot of general challenges or concerns, social concerns of machine learning and ethics, here we have another snapshot which is particularized for fairness. If you Google or if you go into any journal, you can find plenty of them. And basically, what here we see are some examples of some discrimination patterns that we have observed already in the use of machine learning or data science in the real world. So to start with, I'm going to go in detail a bit more into two particular examples. The first one is about recidivism, okay, pretrial bail. So basically, I'm not sure how many of you are familiar with the Compass tool. Nobody in the US? Compass? Yeah? 3, 4? Okay. So for those that don't know, basically in the US, there is a tool that has been already used in which basically they take offenders, they take people that has been arrested, and then based on a set of features, they have some sort of a predictor that given a set of features, find a set of features, computes a risk score for every subject. And based on that, they use this risk score to decide whether they are going to bail before trial, or they are not going to bail before trial. That means whether the offender is going to be released from jail before trial or not. So what they did in the Compass, or in the ProPublica study, was to collect data from people that had been arrested, all the people were let free, and then they checked whether in the next 2 years they were reoffending the system, right? And for all these people with the features that they are using, they computed this risk score. And what they found in the ProPublica study is that actually the people that were labeled as high risk but didn't reoffend were for white people, while almost 45% for black people or African American. In the other way around, the people that were labeled as lower risk but actually did reoffend within these 2 years period were almost 50% for white people, white Americans, while it was 28% for Africans. So who does see a problem in these two? Who would like to be Afro-American and be predicted with these two? Okay, so it seems, which is a bit problematic, that actually what we can see is that the error patterns that we are having here are completely different for two groups of the population. And actually, what it translates, in fact, is that we are keeping in jail the double amount of Afro-Americans that are offending the system than to the white ones, and in the other way around. So it seems some sort of discrimination, right? Similarly, I'm not sure, I hope this is visible. So basically also Google has a face recognition tool, and what we detected was that the error for this group, which is darker skinned female, right? It's a way higher. It's in the order of 20%. It's a way higher than with any other group. That means every time that we need to run a face detection tool, they get a 20% error while the others get something around 5%. Imagine you go to the airport. I do that quite often, and in some countries I still need to do the face control with my passport. And if this face, I need to go to the security man. This is all my time, right? Every time this face, I need to go to the security man, to the policeman, and say, this doesn't work, please let me in, right? So, and this is only happening for females with darker skin. Basically, there was a study and everything, and it turns out that they didn't have any example of Afro-American females in their data set. So, of course, they never saw such a person. The system is not working. Then, so in general, these are two examples, but you can come up with any other type of examples. So what machine learning, after we got several news, and after we realized that somehow everything that we are doing is not purely science that only end up in a paper, but it's having some impact in the people's life, what we decided was to say, okay, maybe we need to look at fairness at the level of machine learning. So the first question that one should ask when we talk about fairness is that what actually it means to be fair, or to be fair in machine learning. Something I want to remark here is that most of the works in fairness in machine learning has focused on one particular definition of fairness, or unfairness actually, which is discrimination. If you talk to a social scientist or a philosopher, there are many definitions of unfairness, but most of our work is focused on discrimination. So one potential definition of discrimination is the one that we see here from Altman in 2016, which is to actually wrongly impose a relative disadvantage on persons based on their membership in their social salient group. Like, for example, sharing a gender or a race. The two previous examples that we saw are an example of discrimination according to race, skin color, right? Because we had a relative disadvantage. So we were releasing much more guilty whites than guilty Afro-Americans, and in the other way around. And the salient social group would be their skin color. So the question here is that now we have defined discrimination, but I have a natural language definition of discrimination. So how do I make my machine learning algorithm to understand what discrimination is, right? So this is actually the first challenge that we have. How do we translate this definition into a measure that we can quantify from observational data? Right? When we measure accuracy, what we do is to take the expectation of the right decisions or the right predictions that we make. And I need something equivalent in terms of fairness. I need something I can quantify because this is the only way in which I can somehow communicate with my algorithm. Right? So this is going to be, of course, our first challenge. And the second one is again, I have a measure of fairness. Actually, how do I incorporate these fairness constraints or these fairness needs into my algorithm, right? Most of our methods, if we think of classification, which is going to be what we are going to see mostly today, what we do most of the times is empirical risk minimization or minimizing empirical loss. So how do I incorporate fairness in this framework? This is going to be the second part of this tutorial. So one might wonder why discrimination. I would say here, and this is my personal opinion, there are two reasons. One is legal or social, and the other one is technical. First of all, from the social or legal one, it's mostly because wherever country you go by now in the world, most of them they have anti-discrimination laws. And they have defined what a social salient group means, being, for example, race, skin color, national origin, age, gender, religion. There are plenty of them. So it is something a bit easier. It seems a bit more objective because once you are given with a discrimination law, you know what features you need to care about, right? So that said, one we're going to see it a bit later. The first question that I think we should address is actually where does this discrimination, these examples that we just saw, where does this discrimination come from? What is the reason behind that, right? So we are going to cover what several of us call sources of unfairness. And the first one that we should consider is that actually human biases, stereotypes, and everything, they are also encoded in the data that we collect. So here I placed an example quite famous in social science about, it's quite of a catastrophical example, but there has been some studies that where you make this puzzle to people, and it takes quite some time for some people to realize who the doctor is and why he cannot enter in the surgery, in the ER. How many of you have seen this example before? Okay, for those that know, that didn't, does anybody can tell me who is the doctor that cannot enter in the operation room? Any idea? Nobody? Huh? Sorry? The grandfather. Yeah, it's the mother. And this is exactly one of the stereotypes that we have when we think of doctors. Somehow, if I think of a doctor and I think myself, the first image I see is a male doctor, right? Today, if you think of a machine learning scientist, and I guess based on the last week that you have had, if you think of a machine learning scientist, probably until I came up here, it's also male, right? So this is exactly what I mean. It is encoded in everybody. We all have stereotypes. It's not that we need to blame ourselves for that, but there are a lot of social stereotypes that whenever we collect data, they are transferred to this data. So the second source of unfairness is that actually the world is quite complex. But in machine learning or in any algorithmic that we carry out, that we deploy, what we do is that we summarize the world with a set of features. So for example, if we are going to make predictions or take decisions about people, we take each of our users, let's say something that is very controversial, a user in Netflix, right? And we summarize them with a set of features. This set of features is finite, right? So we only have a given set of features. So whenever you have trained a neural net, you don't have an infinite number of features. You usually have something between some tens and some thousands, but that's it. I'm not quite sure whether even 1,000 features would fully define who I am. And definitely not the world and all the interactions in the world, right? And something that has been already studied is that whenever we collect these features, we usually do feature collection in order, for example, to perform a predictive task. But it has been already proved that it's quite common that these features somehow are accurate or are representative for some majority groups in the population, but they might not be very representative for some minority groups. Let's see an example. So for example, if we are trying to find a proxy or a good predictor of whether someone is in machine learning, right? Something to look at, maybe it's their GitHub or their Stack Overflow, because there is a high correlation. However, me, I guess I'm still somehow a minority in the field. I'm not a big fan of or a big user of these systems. So these features wouldn't be very representative to me. The third source of unfairness is actually the sample size disparity. I'm gonna keep talking a lot when I talk about salient group. I'm gonna be talking a lot about minority and majority, mostly because it flows more natural for me, but something that we should keep in mind is that whenever we have a minority group, what usually happens is that they are less common in a population, right? So usually if you get a sample from the population of a country, usually immigrants of any sort are going to be a minority, mostly because they are immigrants and they don't represent the majority of the country, right? So what's happened here is that, as we know by statistical learning theory, is that when we do, for example, empirical risk minimization, as we collect, if we have an unbiased estimator of this empirical risk, as we collect more and more data, our error keeps decreasing, right, until we achieve some plateau. But of course, this depends directly on the sample size. If we collect data that are uniformly sampled from our population, in order to be representative for the minority class, we are going to need to collect much more data, and the error that we might have for them might be much larger than for the majority class. This is a bit of the example that we have with the face recognition in Google, that if you have never collected faces from dark-skinned females, or only you have a few, we are going to be more around here. While for the people that we got a lot of data, we might be more getting towards the convergence. So the other problem is actually that most of our results assume or are based, or our theoretical results are based on the fact that we have a representative sample of the population, right? So that you got something that represents everybody. This is where all our, again, statistical theory holds. At the moment, our representative sample, or our sample of the population, is not representative, but instead it's skewed. It may happen that we have a bias, and we propagate this bias in whatever. Is this clear? Let's imagine that we want to represent the world population, right? And we want to get samples of the use of online systems, right? I have the feeling that completely developed countries, we might get much more data than countries where technology hasn't arrived up to the same level. Let's say another example, I'm not sure right now. I would need to think, but basically, what we might not be able to ensure is that we have sampled uniformly from the overall population, but we have only a biased sample of it. And this is where the actual data collection process also comes in. Something that we are going to see more like by the end of the fairness is that actually some of the decisions that we make might induce directly a bias in our data collection process, and this is going to have very harmful effects. Another point that I'm not sure whether you have ever thought is that while in general, for example, when you make a human make a decision, something that is very common in some countries, for example, in the UK, when you submit your CV, in general, they remove any information that can tell any information about, for example, your gender. They remove your name, they remove your gender, they remove information about these sensitive attributes or the information about which social salient group you belong to. And by doing that, if the decision is made by a human, in general, you have removed some sort of discrimination in most of the cases. However, what we are going to see is that this might actually not be enough in the case of machine learning. Because actually, machine learning, what it is very good at is at finding proxies. So let's imagine that I have removed the information about the race or the skin color of the people. But then, it is well known also in the US that people tend to gather into neighborhoods according to which social group they belong to. So if I remove the race information, but I keep, for example, the zip code, the machinery is going to very easily learn that there is a high correlation between where they live and their race, and it's going to use this information that in principle we didn't want to use in order to make decisions. This is what we call proxies. So it might be not enough to remove the features that might seem to be sensitive because a lot of information about these features might be encoded in other features. Another example is that if you, for example, which is a bit more indirect, if you take information about my height, the probability of me being a female is a way higher than me being a male, mainly because I'm quite short, right? So, in general, what we have seen so far is that actually we saw some examples of unfairness or discrimination triggered by machine learning algorithms, and we saw that these examples can have a reasoning or a cause for many diverse scenarios. And I have mentioned a few, but I'm quite sure there might be quite a few more. So the other that I've been talking about unfairness or discrimination, I gave you a high level definition, but now is when we are going to go more into the detail of fairness definitions, at least in the context of machine learning. Because I said that challenge one was how do we translate a definition of fairness into a quantifiable measure, right? So coming back to our definition of unfairness, which is discrimination, I'm going to say that in general, from a social and legal point of view, there has been discussed two ways of discrimination. One that is at the individual level, and basically what it says is that individuals should be treated by a decision-making system consistently and independently of their social salient group. So we are going to be looking at fairness at the individual level. Is this individual being treated in a fair way? And the second definition, which is where we are going to spend most of the time, mostly because we are going to see that technically it's way easier to handle, is actually group fairness. And usually it focuses mostly on the outcomes, like some statistical property of the outcomes of a decision-making system, which should not systematically differ from different groups, right? So in the examples before, we saw that the errors that we were having in the significantly different for different social groups. Okay, so let's start with individual fairness. So there was a paper from 2012, which is basically the most relevant work so far from my point of view in individual fairness, where they say that actually similar individuals should be treated similarly. So basically, what they actually do is they assume that they have a machine learning model, this M, that maps from the input space, which we call X, to the space of the outcomes, this one here. And they assume that they are given with a similarity metric in both the input space, which is this lowercase d, between two input feature vectors in the input space, and another similarity metric in the output space. And they say output space should be upper bounded by the distance in the input space. That means if two individuals are very similar in the input space, in the space of the outcomes, their outcomes should be as similar as in the input space. Let's say you have two people with the same set of features that only differ, for example, in gender. And I'm computing the risk score of reoffending in pretrial bail, the COMPASS example. So the risk score, if they look very similar, cannot be completely different. It cannot be 1% probability for the male and 100 for the female. That's exactly what this means. Is it clear? So what they actually prove in this work is that actually any predictor that is Lipschitz, basically any predictor that somehow is smooth between the input and the output and in the space of the outputs fulfill these criteria. The main problem that we have here, and nobody seems to have raised so far, is that we are assuming that we have a similarity metric in both the input and the output space. So how do we actually assume that the input space is the set of features defining people? How do we actually define a similarity metric between people? Are we more similar because we share gender, or because we share age, or because we share country, education, interests? It's not quite easy to define similarity when it turns out about people. Something that also they remark is that when we make a decision, in principle, socially talking, you would like that this decision is somehow deterministic, so you don't have the feeling that you go today to the bank and you didn't get the loan, but maybe if you would have gotten tomorrow and you would have gotten another sample from your random generator number, you would have gotten the loan, right? So socially, we would like to have deterministic decisions, but exactly in the definition that I said before, this is not possible if we want to achieve individual fairness. So here we have an example. Let's imagine that we have people here in this risk score. Let's assume that we are happy with our risk score. And this is the probability of a positive decision, right? So I think if in a deterministic case, it's quite clear that people that are approaching this threshold from the left are very similar to the people that are approaching this threshold from the right. They are very, very similar. However, they are getting completely different outcomes. Would get a positive outcome while the others wouldn't. So this deterministic decision-making system will never fulfill fairness. So one of the main results that they got is to actually say that in case we want to achieve individual fairness, we are going to need to introduce some stochasticity, some randomness in the decision-making process. And this is exactly what I'm representing in the right figure, where we have like the probability of everybody getting a positive or a negative response is actually a ramp. And then you would, every time you would apply for the loan, you would get sample, a decision with a probability that would depend directly on your risk score plot here. So there are some other papers on individual fairness. I'm not going to really enter much in details here, but this is most of the main definitions. One of the main results where we, for the first time, check and make the decision that if we want to be fairness at the individual level, we need to include some stochasticity. And there has been some few works trying to get algorithms to achieve individual fairness beyond this example that I was showing here on the Leipzig conditions. There are some of them based on bandits. There are some others based on causal reasoning. I'm not going to enter here there, but if you are interested, I'm happy to give any references during the breaks. So, as I said, I was saying that I'm going to only touch a bit individual fairness, but we are going to mostly focus on group fairness. And coming back to group fairness or group discrimination, what we are going to focus now is actually in some properties of the outcomes of a decision-making system and how they behave for different groups. So something I like to make a distinction when we think of discrimination. Yes? This one? Yes.
I'm having a little bit problem to understand the individual fairness might be achieved with a randomized system. For example, if I am a Latin person, I don't know, but I go to the US and they tell me, okay, maybe you committed a crime, or no, you are close to the threshold. So to make it fair, I will just toss a dice or something to avoid making any bad decision because you're Latin or not. I am having problems to understand why this randomized thing, I understand it in the technical community, but when you apply it to real cases, I don't see how this will actually bring the fairness.
Okay, so let's assume, right, that this risk score that we have plotted here is directly proportional to your probability of reoffending or your probability of not repaying the loan, right? It's probability. We will never get to observe whether you repay the loan or you reoffend if we don't grant you the loan or release you from jail, right? So what we are assuming is that something that you could do is to compute this risk score and say everybody that has a risk score that is higher than the cost of this person not repaying, right? Then don't give them the loan. This is what a deterministic one means. The problem that we have here is that these two people here in the limit from the left and the limit from the right, they have very similar probabilities. So maybe one is 0.49 and the other one is 0.51, right? However, with a deterministic threshold, everybody in these locations are getting completely different outcomes, right? So what they are saying is we should instead randomize our decisions and give someone alone or grant someone alone with a probability which is proportional to their probability of repaying it. And this is what this means. So basically, and this is only based on point estimates, but you can think also that whenever we get this risk score, there might be some sort of uncertainty around the point estimate. So there are several algorithms. This is a very simple one, which is I introduce randomization and I sample according to your probability, which is computed by the risk score. There are some others that are more based on statistical tests and say, okay, if I don't have any statistical evidence of two people being different, because, for example, their uncertainty overlap strongly, then these people are going to be treated with the same probability. But basically, what you cannot have is decisions that, with very small differences in the input space, get systematically, there is systematically here, completely different outcomes. While if you think in terms of probability and when you are sampling from this coin with this probability, in expectation, everybody is being treated similarly if they are similar. Is it more clear now? This is something that we could enter there. This is a big debate that I'm having already with social scientists and philosophers. We know technically that we need some randomization. The question is which kind of randomization is doable from a social point of view, right? Because somehow it feels, from an individual perspective, it feels a bit unfair if there is noise in your system, which is this probability. But on the other hand, you can think this noise as the uncertainty about who you are, right? Nobody has a real function that maps who I am into me repaying or not the loan. Not even myself, right? So there is already this noise. The question is how to incorporate it. That's an open social challenge. We know that from a technical point of view, we are going to need randomization. And we are going to see that several times over the talk. The main question now is how do we implement this randomization? So this is a very good point. Okay. So coming back to group unfairness or discrimination, so something I was saying is that actually, I usually like to divide the different contexts into two different scenarios. So whenever we make a decision, there might be two scenarios, some in which we get some sort of reinforcement or we get some additional information about whether our decision was right or wrong, whether we made the right decision or not, and some others in which we don't get that information. So in the case of the loan request, whenever we grant a loan to someone, only if we grant a loan to someone, we get to see whether they repay the loan or not. And this is an objective observation on whether our decision was right or wrong, right? Because if we gave the loan to someone that didn't repay, then maybe we didn't take the right decision. However, there are some other scenarios where this objective outcome is not directly observable or it doesn't directly exist. So I usually like to think in hiring processes. So whenever I hire an intern, a PhD student, a software engineer in a big tech company, there is not such a measure of whether this hiring decision was right or wrong. There are only very few cases in which you can say that the decision was wrong. In general, if you ask me whether I'm happy with my students, yes, I'm happy with all of them. All of them are completely different. So I don't have this objective measure of whether my decision was more right or more wrong. It doesn't even make sense from my point of view. So I'm going to divide the different scenarios into these two settings. And then we are going to study different definitions of fairness that actually apply in each of these scenarios. So let's start with the fairness without ground truth. For that, let's assume that I'm in the hiring process, so that whenever I have some applicants for my internship problems, I collect some features, usually their grades, the university, previous project, so on and so forth, which I categorize as non-sensitive features, which are the sexes, and then I might have some information about their sensitive attributes, for example, about their gender or their race. Together with that, I can look at the historical hiring that the MPI has had in our internship program and see which of these profiles we hired for an internship and which didn't. And in order to automate this process, in order to be looking at all this data by myself, I can apply a filtering tool that decides whether I would hire a person or not. So that we have these features, we have this observed later, and using a learning algorithm, we try to make predictions in an automatic way. Right? As I said, this is going to be a challenge in the sense that here, whenever I make predictions, everything I try to do is to map my predictions to the previous observed labels or the ones that have been made by the rest of my colleagues. In this context, where I don't have access to whether the decision was right or wrong, two of the legal definitions of discrimination that actually apply here are parity in treatment or impact. They are also known as disparate impact, disparate treatment. They mostly come from US discrimination laws, these terms. And this is what we are going to define next. So starting with parity or equality in treatment, or it's also called an awareness. This definition means is actually the outcomes should not change with changes in the sensitive feature. So if we talk about probabilities, what we have here is that the probability of our prediction given X and the sensitive feature should be equal to the probability of the prediction given X. That means our decision should not have a direct impact in the decision that we make, right? So I cannot change the probability of whether I would hire someone or not based on whether they are a male or a female. That's what disparate impact means. So that, for example, in this example, we have two candidates for our internship program, which one of them is a male, one of them is a female. If I have their grades, their coding skill, and prior internships, they all have the same set of features. The historical decisions that we made, where we only hire the male applicant but not the female, would suffer from disparate impact because their set of features is exactly the same, and the only difference in the probability of hiring them has come from the fact that one is a male and the other one is a female, right? So in order to remove disparate impact, I would either need to hire the two of them or none of them, according to my predictions. So this is also known as direct discrimination. So disparate treatment is equivalent to what it is socially known as direct discrimination, which is I shouldn't base my decisions or my predictions based on some sensitive features or which social salient group you belong to. Yeah.
When you did this, removing the feature, but you still have the proxy program, right?
So this is exactly what I was about to talk now, which is there is a very easy way of getting rid of disparate treatment, which is we don't use the sensitive feature at all when we make our predictions. This is in the example I was mentioning before, when you submit your CV into the UK, into a public UK system, all this information is removed and is free of disparate treatment. But then, as you rightly pointed out, then we might have the problem of the proxies, right? This is exactly what the second definitions of unfairness or discrimination at the group level tries to avoid. This one is called parity or equality or demographic parity in impact. And what basically says is that the probability of getting the positive decision for the different groups should be the same. Everything that it's saying is that I should hire the same number of female, or not the same number, the same probability or proportion of female applicants than male applicants. So if we get a look to this data where we have plotted the grades and the internships of the applicants, then we have the gender, which is the sensitive feature, and then we have the historical decision. Cross means we didn't hire them, they apply but we didn't hire them. Tick means we hire them. In a classifier, automatic algorithm that would mimic our previous decisions, right? What it would do is to have this almost vertical margin where 60% of the males will hire, of the male applicants, while only 40% of the female applicants will hire. This classifier would achieve a 100% of accuracy based on our historical decisions, okay? But of course, it is suffering from disparate impact because basically there is a mismatch between the probability of hiring female applicants and male applicants by 20%. Is that clear? So now, basically what it may happen is that since I don't have in principle any reason to say that the male applicants are better than the female applicants if they share very similar features or in proportion. Basically what I could do is to actually enforce that my classifier, my future predictions, fulfill demographic parity. And then what I would get is this blue, like diagonal threshold, where I would hire 60% of all the applicants, males or females, and I would actually have a reduce in my accuracy with respect to my previous decisions to 90%. Basically because this female that is here, and I was not hiring before, I would hire under my new decision policy, right? Something that is remarkable here is that actually what this fair classifier is doing is actually putting different weights to the feature space, right? While before most of my decisions, or all of my decisions, because I almost have a vertical line, were based on whether the applicant had a prior internship. Now, what I'm saying is that it doesn't really matter if you didn't do a prior internship, as long as you have a very good grade in your bachelor, right? So this is what's semantically. Okay, so something that someone there pointed out very clearly is that here what we are doing is to correct for proxies, for some indirect correlations in our data, and this is also called indirect discrimination. So it might be that because of the fact that there were always more males in computer science, we have seen all of their profiles and we know that we like how they work, and somehow we had this bias in the data, and now we try to correct for that because we were having some sort of a reinforcement in the people that were already did an internship to give them a second one, while we were not giving too much chances to people that never did an internship, even though they had very good grades. So in order to correct for disparate impact, or in order to achieve parity in impact or demographic parity, there are like hundreds of names. I'll try to repeat them so that you get familiar to them. Basically, here there are three main ways in which you can achieve demographic parity. The first one is that we have some data, some historical data, and as I said, they might have some sort of correlations between our sensitive features and the decisions that we made. So what we can do is to make some pre-processing step to correct a bit of the data to remove that correlations. Basically, you change a bit your data. The other option is that once we have made a decision, if these decisions are biased or these predictions are biased in terms of disparate impact, what we can do is to correct actually for the predictions so that they achieve demographic parity. So for example, that means if I have predicted that I would only, under my decision, I would only hire 40% of the females and 60% of the males, I could change some of the labels that I assign to the females to be positive so that I achieve 60%. And the other one, which is in the line of the example I was having, is that we could modify the training of the classifier to account for the fact that among all the potential solutions, all the potential decision boundaries, you can have an infinite number of decision boundaries here, right? That achieve demographic parity are allowed by adding some additional constraints during my learning. How are we with time? Half an hour, right? Good. So these are the two main definitions that has been proposed when we don't have ground truth observations in our outcomes, and where these biases might be triggered because of some historical reasons. And when historical reasons, I mean examples like the one that we had about the doctor, that somehow all of us tend to think that a doctor should be a male by default, and then whenever we make our hiring processes, we might propagate this into our data, right? But now we are going to change to a new scenario where I'm going to assume that together with my set of features, yes?
These features, is it possible that there could be bias in picking which features are thought to be sensitive?
Yeah, well.
So on slide 22, we have great coding skills and intelligence, and then you have the gender on the left. So could it be that you have lower grades, but we can still be whatever good intern? That's a bias too.
Yeah. So yes, I'm going to give you in a bit an example. So this is exactly why I'm remarking discrimination, because discrimination laws directly establish. These are the ones that I saw in a previous slide with. There are a few more, but anything out of these discrimination laws is not directly considered as discrimination. Might be considered still unfair, but not directly discrimination. So this is why I keep remarking that we are in discrimination, because what is sensitive in this context and what is not is defined already. But you have a very good point, and there is actually nowadays a system where they have, I'm not sure whether you are familiar, but in China, they have implemented a system that score, as far as I know, I might be wrong, that score people about how of a good citizen people are based on their data that they collect. And what they detected is that video gamers are usually scored with a higher risk of being a worse citizen than not video gamers. Well, but of course, according to discrimination laws, video gamers are not protected. They are not considered a social salient group. And you can, of course, enter in the discussion of whether it is okay to put video gamers just because they are like spend their spare time playing video games on a higher risk for society. That I'm not going to even enter there. But yeah, you got a point. So coming back to where we were, yep.
So your suggestion to adjust this see whichever feature drops, right, in order to keep the rate fixed. So in order to, do I understand it correctly, in order to introduce, do not introduce the bias again by accepting less qualified candidates from the other group.
So yeah, you can interpret this correction as weighting different the features. Also, you can also interpret it as, actually, let me see if I can go. As actually trading off a bit in a different way through positive and false negative, so you can move people around. And yeah, under different scenarios, we are going to see that later. That might be even more unfair than the setting that you had before, right? So I'm providing definitions. These are the main two definitions that are in most of the laws, discrimination laws. It seems that they have some handicaps when we talk about fairness, at least in an algorithmic perspective, where we have simplified our setting and we only identify people as a subset of, as a finite set of features, and everything is a matter of how I weight these features, right? Yeah, we are going to see plenty of problems. That's the whole point of this. Okay, so any other question before I go back? No? Okay, so far, as I said, these two definitions are two main definitions that are mostly implemented in every law, at least European and US law that I'm aware of, in a way or another. And big historical or social reasons. For example, if we think in social reasons within the context of the US, where African Americans, basically they got the rights a way later than the non-African Americans, than the white ones. Basically, if you see what they are trying is to correct for all these historical biases. But of course, if we apply them into different settings, it might be that when we are trying to correct for unfairness, we end up in a scenario that might be even worse than before. We are going to see some examples. So now, moving into scenarios where I have a ground truth, so I assume that given a decision, I can get to see whether my decision was right or wrong. Then, most of the definitions of unfairness or discrimination, what they focus is basically on errors or predictive rates, so that we correct for scenarios of the sort of the compass or the face recognition problem that we saw at the beginning, that suddenly for a subgroup of the population, we were having completely different errors than for the others. So one potential definition in terms of errors where we have ground truth is what we call parity mistreatment. Basically, it accounts for the fact that errors should be the same across all sensitive attributes. That means the probability of our prediction and our true label differing should be the same across different groups. That's what it means. So if we go to this example, where we have men and females and feature 1, feature 2, here I don't need to really enter into an example, what we see is that for males, if this is the positive class and this is the negative class, we have a false positive rate, because we are all these people that should be negative, we are classifying them as positive, which is a way higher than for females, that is 0, while in the other way around we have a false negative rate for those females that were classified as negative while they should have gotten the positive outcome. That is exactly what I was saying in terms of the compass. So basically that could mean that white people have a higher probability of being released and still reoffend, while Afro-Americans were having a high probability of being labeled as high risk but still not reoffend. So of course, when we talk about errors, we can, here I have measured errors in terms of overall errors for the people, but here we can measure errors in terms of false positive rates, false negative rates, any kind of combination that you can come up with. And depending on the scenario, some applications will make more sense than others. Similarly, we can think instead of errors into accuracy, probabilities, and for example, some of the more accepted definitions in the literature, one of the most famous ones so far is the one proposed by Moritz Hart, I have mentioned him before, in Berkeley, which is equalized odds. Basically, it says that the probability of the positive outcome condition on the true label, right, should be independent on the sensitive feature. Basically, condition on the fact that I'm going to repay the loan, the probability that I'm granted the loan should be independent on whether I'm a male or a female or I'm white or not. This is what this means. Yep. Another definition, which is a bit of a more relaxed and easier to achieve definition, also proposed in this same paper, is actually equal opportunity. And now what we are conditioning is not on whether I would repay or not the loan, or my true label in general, but only for those people that actually would repay the loan. So if I deserve the loan, the probability that I get the loan should be independent of my sensitive features, which social salient group I belong to, right? So they are basically very similar. The only difference here is that here we have Y in general, which is the label, I would repay or not the loan, and here I only restrict myself to the people that would repay the loan. Good. Of course, here what we have now is that there are three main variables that are interplaying. One is my prediction, which is this Y hat. The other one is Y, which is the true label. And the third one is the sensitive attribute. Before we were talking about disparate treatment and impact, there were only two variables playing a role there, which were predictions and sensitive features. But now here we have ground truth. So there are different ways. Parity in mistreatment or equalized odds or equal opportunity, they are somehow equivalent because when we talk about accuracy in binary classification, accuracy and error rates are completely related with each other. That's why I call it in that way. And basically here, of course, preprocessing the data might not be enough because at the observation level, when I collect the data, I don't have any information about how my prediction is going to behave. So now we only have two ways of achieving parity in mistreatment or in errors. One of them is, of course, post-processing. So I train my classifier, I measure how many errors I make for every group, and I try to correct for them so that I achieve parity. The other way is to modify the classifier so that I find a boundary, like the one I had before, where the errors are balanced, whatever error I define, or whatever discovery, like accuracy rate. Here we have some definitions of fairness, but something I want to remark is that if you think of the ways in which you can evaluate a classifier, which are plenty of them, here we have some ones where we are conditioning on the true label, which is the ones that we saw, false positive rate, or equal opportunity. You can also do it in the other way around and condition on your prediction and see what the outcome would be. In that way, there are another several ways. Something I'm trying to say is that here I presented a subset of the most commonly used definitions of fairness, but there are many more. Actually, there is a tutorial that is called 21 Definitions of Fairness and More. It's quite entertaining. You can watch it online. Again, and I think through the discussion with different people in the room, something that I think hopefully has been already clear for everybody in the room is that there is no such a thing of universal definition of fairness. every scenario, every context, different definitions of fairness may apply and others they might not. So, for example, something I usually think of is that if we have historical decisions, potentially biased, no ground truth, maybe parity or equality in impact or demographic parity might make sense because we are trying to correct for our stereotypes. But in the case where we have ground truth, why I'm going to give the loan to people that I know they are not going to repay, right? So in that particular scenarios, other type of definitions based on errors or accuracy, like mistreatment or equal opportunity, might make more sense for this scenario. So basically, whenever we are going to train a machine learning algorithm that is going to have an impact in society, in individuals' life, we need to be very careful and say, okay, what is my scenario? Fair in this scenario, what do I want to achieve? Before simply in my classifier, 99% accuracy, here we go. So, simply as an example and as a summary, what we usually have or what we did in one of our recent papers was to have some examples where we have some sensitive features about whether people were female or male, some non-sensitive features like about their clothing, and a proxy for crime. That's in a police scenario where they need to decide whether to stop and frisk someone, a pedestrian on the street, whether someone looks suspicious. And then we had, let's imagine that we have 3 classifiers. Each of them is a policeman, right? And they make decisions about whether they would stop and frisk these people. Being stopped and frisked in the middle of the street is not a really pleasant situation, by the way. So basically, I'm not going to elaborate very much here, but you can see actually which of these classifiers suffer from each of the definitions that we have been talking about according to the definitions I have here on the top. And what we can see here is that this is a very toy example, but even in this toy example, there is not a single classifier among the 3 that actually fulfills these 3 main definitions. You see? None of them. So, this is something I'm going to leave here, but we are going to come back a bit later about trade-offs and impossibility results, where we are going to see that actually it might be that you cannot achieve all these definitions of fairness at the same time. But this is a spoiler. So for now, what I just want to do in the last 10 minutes is to actually point out that all these definitions of fairness that we have been talking about can be seen or can be formulated as some sort of statistical independence or statistical conditional independence between 3 random variables: the sensitive features, the target variable, the label, and the prediction that we make about this target variable. So if we have independence, basically our prediction should be independent on the sensitive feature. This is no more than the definition that we had about disparate impact or statistical parity. And someone already pointed out, what this definition is doing is ignoring any potential correlation or statistical dependence that there might exist between the label and the sensitive feature. So if because of the true label and the sensitive feature, so that, for example, applying impact or demographic parity in scenarios where we have ground truth might not be the best idea. Also something that in order to achieve independence, what it allows is to correct for false negative and false positive, so we shuffle people around, we make some more errors, but then we achieve parity. Still, I must say that although it is less and less adopted, this definition, it might still be useful when we want to correct for some historical data, biases or stereotypes. But it does definitely not really apply for scenarios of the examples that we had, like the face recognition or the pretrial bail, where maybe statistical parity doesn't make sense because releasing people from jail that they are going to reoffend, from my point of view, doesn't make much sense. The second definition is separation, where basically we say that condition on our true label, both our prediction and our sensitive features should be independent. This is very related to any error-based classification measure that we have seen, like mistreatment, equalized odd, equal opportunity, all these ones. Good thing of this definition is that this type of definitions is that actually they account for any statistical dependencies between our true label and our sensitive feature, right? So it might still be that because I'm a female, I have lower probability compared to males of being a computer scientist, and as long as these biases are due to the population distribution, they are fine, but not induced by the classifier. We are going to enter a bit later in that. So what it is important to remark here is that all these definitions apply when you have a ground truth label, right? When you are certain that the labels are actually what you want to mimic, whether they repay the loan or they didn't. And there is another type of definition, which is in the other way around. Now I condition on my prediction, and I make our true label and the base and the sensitive feature to be independent. Basically, that would mean statistics to say that condition on the predictions that we are going to make, I need to enforce that my sensitive feature and my prediction and my true label are statistically independent. And I'm not going to really enter here, but something I would like to remark is that this concept is highly related to a concept which is very common in machine learning, which is calibration. Anybody familiar with calibration of a classifier or a predictor? No? Okay. So basically, a calibration in general in machine learning means this. Basically, the probability of the true outcome given your prediction, your score here, R, which is no more than the expected value of your label given X, right? What you are going to predict in expectation for X, should actually be the same, should coincide with the true probability of reoffending. So that simply means, in terms of fairness, that when we have several groups, we don't need only to ensure calibration at the overall population, but we need to ensure calibration for every sensitive feature. So that would mean that we need to fulfill this property when I condition here on set. You see that? When I condition here on different sets. As a visual example, just for completeness, basically the predictor on the left side is well calibrated because basically the rate of the force of the positive outcomes and the score that we get are completely aligned, and they are completely aligned not overall but also in terms of males and females. While if you look at the predictor on the right, there is a bit of discrepancy in the case of black people, right? So for these people, our prediction or our score is saying that the risk is higher than actually it is in reality. And this is something that is not very desired. Calibration, I'm not going to really enter much more about that, but calibration is a property that most of our machine learning algorithm for predictions fulfill by definition. So in general, it's going to be quite of a soft condition, and this is why most of the work that we are going to talk about from now on is going to be based either on independence or separation, but not on sufficiency. Okay, so I have another 5 more minutes. I don't think I have time to really enter into impossibility results and trade-offs, but something that we can take for tomorrow is that I have presented quite some definitions of fairness, And I have presented some examples about how my decision boundary may change when I enforce fairness and what implications it has in terms of accuracy. So something to remark is going to be, first of all, that there will be several definitions of fairness that we are not achieved at the same time. We cannot fulfill both of them at the same time. And second, based on our historical data, when we train, for example, a classifier just to maximize accuracy or minimize loss, this is going to give us a better result in terms of accuracy than when I constrain for fairness. Because there is, in general, depending on the overall data distribution, there is going to be a trade-off between accuracy and fairness. And whenever I want to make more fair my system, I might lose more into accuracy. How much? We will see. Okay, thank you very much.